Hello everyone, and welcome to another fun adventure in statistics. Today I'm going to be going over the confidence interval example sheet that you can find in our weekly folder on Blackboard. Um, so I'm going to get really in depth with the confidence intervals today, so prepare yourselves. Wahaha. So I'm hoping you can follow along with these solutions and help them make sense to you. So I have the answers on here on these examples, but I'm also going to give you more in-depth explanations on this video. So we're going to start with this first question. Use the confidence interval to find the margin of error and the sample mean. So what I want you to be thinking about here, oh, it won't react to my pen just yet. Hold on. Draw with touch. Draw with touch. When you create the interval, so when you're calculating a confidence interval, you take your original mean and you add and subtract it to it, the margin of error. So when you're making the confidence interval to find the upper part, you start at the mean and then you add a margin of error to reach this value, which is x bar plus the margin of error, which we found in this problem, well, was given to us, was 2.02. Okay, and then to make the other end, we do the subtraction one. So we subtract a margin of error, which moves you backwards on a number line, to the mean minus whatever the margin of error has to be. So you land here, which, sorry about that. Clearly my laptop hasn't been used in a while. To get the lower end, which is 6.00. So notice in the very middle of this interval is the mean itself. Aha! Which is exactly why we need to find the center of this, which we can do by doing the average, which that's what I did in this calculation here, is I added the upper and lower limit and then divided by 2. That's taking the average of the two of them exactly in the middle. There's that guy. The other thing worth noticing here is this distance, as I noticed, is a margin of error. So if you're going all the way across here, it's a margin of error plus a second margin of error. So really it's 2 across. So if you do the distance between these two, that's 2 margins of error. So 2 margins of error makes the distance between two numbers. So if you don't remember how to do the distance between two numbers, it's just their subtraction. And just a quick little review of that. Feel free to fast forward like 30 seconds while I review this. The way you know that that's going to be the subtraction of the two of them is if you think about two numbers in the number line and how far are they apart. Like, say you're going from, 2, let's do -2, and that's 0, 1, 2. Okay, so then the distance from 0 to 1 is 1 unit, and the distance from 0 to 2 is 2 units. So you're really doing distance away from 0. But the distance from -1 to 2 is 1, 2, 3. So how do you get that? You do 2 minus 2 to figure out how far away they are from each other. Similarly, let me put 3 on here. If you're trying to find the difference between 2 and 3, you wouldn't say it's from 0, 1, 2, 3. You'd do the distance these were away from each other. So what you're really doing is you're taking the distance 3 is away from 0 and removing the distance you would have traveled to get to 1. So 2 minus 1, which gives you 2. Or sorry, 3 minus 1, which gives you 2. So you subtract these two, divide by 2, that's going to give you that 2.1. Alrighty, let's go back to select. Alrighty, so let's suppose instead you were doing a Gallup poll of 456 randomly selected adults, and they asked if they're in favor of the death penalty for a person convicted of murder. And 296 of them said they are in favor. Fun times in Murderland. Yay, murderinos. Wow, I can't say that word. So again, our idea of success here is going to be being in favor of this particular political item, and so that's our success number, our x, which is that 296 out of our total number sampled. So again, this is a sample proportion, and that's why we are listing this with a p hat. Remember, hats are indicators that, or bars are indicators this is coming off a sample. This is actually why we use x bar up here for means. So if it's got something on its head, it's a sample. Samples on your head, all that jazz. And then to find the 90% confidence interval for the estimate for the percentage of adults who are in favor of the death penalty, we are going to use Minitab to do this. So let's go on over to Minitab. Since I have such a large sample, this is probably going to be a t, but since it's a proportion, it's automatically going to pick it for me. So I'm going to go over to Stat, Basic Statistics. Oh, sorry about that. My mouse is a little more sensitive than I thought. Stat, Basic Statistics, and down to a one proportion test. All right. And then it thinks, hey, is your stuff in my data worksheet down here? It is not. I'm dealing with summarized data. So I got to tell it the number of events. This is my number of successes, and that's 296. And then number of trials, this is your N, the number of your sample size, so that's 465. I'm not performing a hypothesis test, I'm just doing a confidence interval. And then I note that I need to make it a 90%er, so I'm going to hit Options and change my confidence level to 90%. Alrighty. And then I'm going to change this from exact to normal approximation, because that's what I'm actually doing, is I'm doing a normal approximation of the binomial for this proportion. And we're going to hit OK twice. And it's going to come up with this lovely proportion. So notice this is the same thing as what I have in the answer in the Word document. Make sure you follow along with these steps. So again, that's stat, basic statistics, and then one proportion. Yay! All right, so what we want to say is, can we safely conclude that a majority of adults are in favor of the death penalty? Well, yeah, the entire confidence interval is above 50%, so we're 95% confident that it's somewhere between 61.2 and 68.6%, which is higher than 50. We're fairly confident that it's going to be bigger. So, moving on, number 3. In a study, the length of time that a student requires to earn a bachelor's degree, 83 students were randomly selected, and they found to have a mean of 4.8 years based on data from the National Center of Education Statistics. I think it's educational statistics now. I should probably fix that. Anyway, the names of things changing all the time. Woohoo! We're given that the population standard deviation is 2.1 years. We're going to construct a 95% confidence interval for the population mean. Now, big thing, since we know the population standard deviation, we can actually use a z-test instead of a t-test for this, regardless of sample size. Even though this sample size is pretty large, so we probably could use a z anyway. But, you know, there's that. Let's go ahead and open up Minitab and do this confidence interval. So we're going to go up to Stat and then Basic Statistics and down to a 1 sample z. This is the one we use for means, since we were given that we're looking at a mean of 4.8. That's how we know this is the one we're going to be using. And again, this automatically defaults to you must be using data, but we actually have summarized data. We have the values in here. So I have my sample size, which was those 83 students, my sample mean, which is the 4.8, and then I know my standard deviation. So this is known standard deviation. This is how it knows it's coming off of a population parameter. So remember, parameter comes off of population. This is a population parameter. I'm not doing a hypothesis test, so I'm not going to click anything here. And I'm going to be doing a 95% confidence interval, so I need to make sure this is set to 95. It is. We're ready to go. Always check your options before hitting OK to make sure you're using the right confidence level. We're going to hit OK. And there's our lovely 1 sample z, which is the exact same as what's here. So the part you need is this interval right here. So what this would tell you is that the population in general takes between 4.3 and 5.2 years. We're 95% confident that that's the value to finish their bachelor's degree. And this makes sense because a lot of people, when they go to get their degree, sorry about that, they decide partway through, hey, maybe I want to, change my major, or maybe I want to take a semester off. So in general, it's not always exactly 4 years. It's usually slightly higher. And some people will decide to transfer, and sometimes that puts them behind in their program, regardless of what it might be. Okay, so let's say you want to estimate the mean weight loss of people 1 year after using the Atkins diet. How many dieters must be surveyed if we want to be 95% confident that the sample mean weight loss is within 0.5, so half a pound, of the true population mean, assuming the population standard deviation is known to be 10.6 pounds. Alrighty, so in here I used a handy-dandy formula to calculate this, but I want to show you really quickly where that formula came from in case you were unsure. So I'm hoping you remember the margin of error formula is the critical value times the standard deviation divided by the square root of the sample size. Now, if you do a little bit of algebra, you can solve for the sample size. So what you can do is you can take this and divide by your z-star. That'll get rid of those. That'll divide out and make a 1. So I have ME divided by d star, and then I'm going to invert everything. So that gives me z star divided by the margin of error equal to the square root of the sample size divided by sigma. So now n still not by itself, so I'm going to multiply by sigma on both sides. If you ever have a hard time with solving things in algebra, remember it's the opposite of the order of operations, and you also want to think about it like parentheses. If what you're trying to get to is on the inside, you need to get rid of the outside stuff first. So what I'm saying is if you're looking at the square root of n back here, it's being square rooted, and it's dividing by something, and it's multiplying by z. Whatever happens last, you got to get rid of first because it's on the outside of the parentheses. So you work your way in, just like how when you're dealing with parentheses, you start with the inner part and work your way out. They're opposites. You're doing opposite operations. So now I have that the square root of n is sigma times z star divided by the margin of error. Boy, my handwriting's fantastic with this, and I want to undo a square root, so I'm going to square both sides. And then these two will cancel each other, squaring and square rooting undo each other, and then I'll get this value. So sigma times z star. Oh, it doesn't want to relegate my hand motion for some reason today. Try using my finger. Oh, it's picking that up better. There we go. Divided by margin of error squared. Interesting. So that's exactly where that formula came from, in case you were wondering. So when you do this, you get a decimal. And I don't know about you, but you can't have half of a person on a diet. Sad but true. So we always round this up, because if you round it down, it's quite possible that you don't have enough people in your sample to meet that margin of error. It's always better to have a slightly smaller margin of error than what you need, rather than a slightly larger one. Alrighty. Moving on to number 5. Okay, so let's suppose now you have a sample of health employees that are monitoring by periodically weighing them in, and a sample of 58 of them, I should have started with that, sorry I said sample earlier, has a mean weight of 182.7 pounds with a standard deviation of 112.2. So a couple things worth noticing here. Notice that that's little s, so that tells us this is the sample standard deviation, not the population one. So we immediately should think, oh, I'm probably going to be using t, not z. So as I look at this, I'm going to use Minitab to produce a 95% confidence interval. So we're going to go to stat, basic statistics. It wants to do that every time. I'm going to go down to one sample t. Still choosing summarized data because that's what I have. I have my sample size to be 58. I'm going to use my sample mean, which is 182.7, and then my standard deviation, which is 121.2. Why is my voice getting higher? That's weird. And then I want to check to make sure I'm 95%. I am. We're going to hit OK twice, and that'll take us into our confidence interval. So there she is. So then we get asked this question, is it safe to say that the mean weight is under 200 pounds? Why or why not? Well, 200 is in there, and less than 200 is in there. There's things above it in the confidence interval, so you can't really say that it's definitely under 200. There's a lot of possibilities in there. This is quite wide, so there's a lot of options. So we'd say, no, since the upper limit is above 200 pounds, it's possible that the true population mean is actually higher than 200. All right, number 6. Why didn't I bold this one? I did like all the other ones in bold. Evidently, I don't like number 6. Take that, number 6. Anyway, so when 343 college students are randomly selected for a survey, it's found that 110 own a car. Find a 95% confidence interval for the true population proportion of the college students who own a car. So, again, proportion. So this is going to be a Minitab one sample proportion test, and I'm doing a confidence interval. And I know the sample size right there. And then I know my number of successes. Let's get to it. So we're going to go to stat, basic statistics, and down to one proportion, because this is a proportion test. I have summarized data. My number of successes is the number 110 who own the car. And then I have 343 who are in my sample. I'm going to check my options. Oh, it's set back to 90 from that one I did that was 90. I got to change this to 95. Always check this. Go ahead and hit OK twice. And there's my one sample proportion. So I'd say the actual number of college students, actual proportion of college students who own a car is somewhere between 27.1 and 37%. And I'm 95% confident about that estimate. Woohoo! Oh no, we're dieting again. This makes me think I should go on a diet. Definitely. Okay, sorry. In a test, the Atkins weight loss program, 40 individuals participated in a random trial for overweight adults. After 12 months, the mean weight loss was found to be 2.1 pounds, with a standard deviation of 4.8 pounds. We're going to construct a 99% confidence interval this time for the mean weight loss for such a study. Now, two things going on here. I have only 40 individuals, which is a decent sample size, so it's probably normal. However, I do not know the population standard deviation. I actually only know the sample one, so I'm going to have to use T. So let's go to stat, basic statistics, and we're going to have the menus go crazy again because I do this every time. Got to be calm about it. All right. Breathe in, breathe out. It'll be all right. So we're summarize data. Here I got to change my mean. So we're doing the mean difference here, which is a little different. That's why this value is so small. What? It's not an integer. 2. Oh, sample size. 40. Yeah, I can't have 2.1 people. Sorry. I'm thinking of number of successes. I was doing the wrong test. Good job, teacher. Okay. 4.8. Oh, God, I really shouldn't call myself that. Okay, sorry. Let's see. Sample size 40. Mean correct. Standard deviation correct. And then let's hit options. 95%er. Nope, we want a 99%er. No, let's be confident about this. Let's hit OK and OK. And there we are. So we're 95% confident that the entire population on this diet weight loss program would lose between 0.045 pounds and up to 4 pounds. A little bit over 4 pounds. Pretty nice. Wouldn't want to be in this group. Might lose like nothing, which is another possibility that's in here since 0's in there. Darn it. So that says, oh, shoot, that went really fast. So since 0's in here, and, oh no, 0 is not in here. If 0 was in here, there we go, that's what I was trying to say. If 0 was in here, you would be able to say that it is possible that maybe this weight loss program does nothing. Sadness. Anyway. A state highway patrol officer wishes to estimate the number of drivers that exceed the speed limit traveling on a certain road. The last time this was checked, about 28% of drivers were found to be speeding. What sample size is needed in order to make sure that we're 90% confident that the sample portion will not differ from the true proportion more than 2%? So this is using another sample size calculation. So that was our formula that says that n is equal to p times q with your z-score and your standard deviation squared. This is doing by hand. I looked up this 1.64 on the table, but what you can also do is if you go into Minitab and choose Graph, Probability Distribution Plot, Probability View, hit OK, and go on the normal with the standard normal value, you can actually do this by using the middle probability. And since I'm looking at a 90%er, I'd have 5% on each side. There we go. Because it's 90%, which means leftover in the two tails would be 10%. So leftover in one tail would be 5%, and leftover in the other would be 5%. So that's where these two are coming from. And if you hit OK, there's another way you can get that value if you don't know how to look it up. Good times. So that's one of the ways you can find critical values. And then the margin of error was given to us. You pound it that way into your calculator. Be careful with your order of operations. If you're coming up with something weird, divide first, then square, multiply, multiply. Work your way from the inside out. And you get something that's a lovely decimal. My advice to you when you're doing this is to not round until the end. So I'm not saying like... So what I'm trying to say is if you do this division, you get a decimal, don't round it. Immediately hit the square key. And then this, and then that. Does this make sense? I hope so. All right. And then we'll round this up to the 1364. Remember, always round this up. Always. Regardless of what you might be thinking. It's not the 8 that's causing that. Just the fact there's something there. You're going to round it up. Okay. So, of 125 randomly selected adults, oh my god, I wish it would stop doing that. 70 have health insurance. We're going to construct a 95% confidence interval for the proportion of adults that have health insurance. So remember, we're taking sample and we're inferring about the population. Can we conclude that a majority of adults have health insurance? Why or why not? Let's take a look at this sucker. All right, so 95%, we have a defined success and a total number. So this looks like a proportion to me. Yay! Also, there's the word proportion in the question. So let's go to stat, basic statistics, come up with a one proportion test. We have summarized data again, so I have 70 people that have health insurance out of 125. And then I'm going to change this to a 95%er. Oh, it's already set to 95. Good, good, good. All right, let's hit OK. Doot. There it is. So what we'd say is that the true proportion of people who have health insurance, I'm sorry, adults, not people, is between 47.3 and 64.7%. So since not everything is above 50%, that's not a majority. So it is quite possible that we get something that's lower than that, which would not be a majority. So since not the entire confidence interval is above 50%, we would say no, it might not be a majority. Okay. Alrighty. A doctor wants to estimate the serum HDL cholesterol of all 20 to 29-year-old females. What sample size must she select in order to be 95% confident that she has the true mean within 2 points of the sample mean? The population standard deviation is known to be 13.4. So, and this is another sample size calculation. This is pretty typical. I showed you how to get this formula earlier, so we just need to set this all up. That 1.96 is coming off of a common table, or you can use the graph probability distribution plot to come up with that value. As always, do the inside first, so I would do the numerator first, divide it in half, and then square it, and you come up with this number. And again, we always round up. You might be tempted to, remember, since this is under 5, to round down, but always round up. Always. I wish I could make this like Flash, so you'd be like, Luke, pay attention to me. Always round up. Good times. All right. I'm getting dramatic today. I need to calm myself down. Anyway, so suppose we look at a recent study of 68 8th graders, and we find that the mean number of hours per week they watch television is 19.1. That's a lot. Sometimes when I borrow this data from different sources, I'm shocked by what I see. With a standard deviation of 3.8 hours, we're going to find the 90% confidence interval for the population mean. So, in looking at this, I know the population standard deviation, so this is just screaming, hey, use a z-test, and it's a pretty large population size, so we're going to go ahead and hit stat. Basic statistics, go down to a one sample z, and I have summarized data, so I'm going to put in my 68 8th graders, and change this to 3.8, so it has the correct standard deviation in it. That is not the standard deviation, that's the sample size. I keep trying to put the wrong stuff in here. What am I doing? There's my known standard deviation. I get so excited about the standard deviation, I just can't contain myself. And then I want to do a 90% confidence interval, so I want to hit options and choose 90%. 90%. We're going to hit OK twice. Always check your options, man. Know what's going on. And there's our confidence interval. So what this says is that we are 90% confident that the entire population of 8th graders will have a mean number of hours per week of watching television between 18.34 and 19.858 hours. Whoa. Let's talk about some eBay action. I wonder if that's supposed to be a little e. Oh well. So, a manager for eBay wants to determine the current percentage of U.S. adults who now use the internet. My father recently discovered the internet. It was a wonderful thing. He uses it to look at cars all day. It's a good time. They want to find how many adults must be surveyed in order to be 95% confident the sample percentage error can be no more than 3 more percentage points. Assume no prior knowledge for the value of the proportion. So, when this happens, you assume the worst case scenario, which means I'm going to use 0.5 and 0.5 for my Q and my P. If you want to see why, it has to do with the quadratic equation, which is kind of fun. Maybe I'll show that to you. So maybe don't watch the last 3 minutes of this video. So real quickly, I'll do this calculation, then I'll show you why it's 0.5 and 0.5. So P times Q times your z divided by your margin of error squared. Remember, do this calculation first, then multiply, because that guarantees that you won't have any screw-ups. And remember, always round this up. Don't forget that. So if you're wondering why 0.5, I was going to say skip to the end, but I know I have the Minitab portion next. So let me show this to you real quick. Draw with touch, colored blue. So P times 1 minus Q. The biggest these both could be would be 1. So this is probably, since these are both proportions, this is less than or equal to 1. This gets complicated quick, so prepare yourselves. I need to erase that. Sorry. That was Q. But Q is actually 1 minus P. So when you distribute this through, you get P minus P squared, which is less than or equal to 1. And then I'm just going to add these over to the other side. Well, in that case, subtract. So again, I'm doing this. You do not have to know how to do this, but those of you who like algebra might find this interesting. So 0 is less than or equal to p squared minus p plus 1. And wow, this is on such a steep angle. That's kind of fun. I'm going to make some room. Okay, so as you look at this, I have a quadratic, which, as you know, it's bigger than or equal to 0. And what you're looking at here is you're like, oh, so when is this going to be the biggest? What's the worst case scenario here? When is this the largest? Well, to figure that out, sorry, I keep trying to scroll down and it wants to scroll over. We want to complete the square. I know, right? Do you guys remember completing the square? So I'm going to come up with a square, a perfect square that gives me this, and then I got my plus 1. So I want something that when I square this out, I get p squared minus p, and whatever I add is going to have to be good enough that gives me the correct values. I did a better version of this when I was doing other things. So the thing is, when you're squaring, you end up with p times itself, that gives you the p squared, p times whatever you end up over here, so I'm going to write a minus sign in here. I don't know what this value is. And then this value times p, and then this value times itself. So I'm going to pick a half. And the reason why is because when you FOIL this out, like I just said, you do p times p, and that gives you a p squared. You do p times a half, and that's minus a half p. Sorry. Minus, and then you do a half times p, so that gives you a minus a half p. And you do minus 1/2 times minus 1/2, which gives you plus a fourth. Now what's interesting about that is if you add a negative half p and a negative half p, you get this p. So I'm just trying to create something that's equal to the thing about it. But it's not, because I added in this fourth. So you fix that by subtracting a fourth. Ha! So when this is all said and done, you have the following equation. P minus a half squared plus, and then you take 1 and you lose a fourth, and you get 3/4. Now, one of the things we know about quadratics is that they are largest at their vertex. For this, the vertex, since I now put it in complete the square form, is when this is nothing, because this is a minus. So p minus a half. So the vertex is 1/2, comma 3/4. So this is largest when p is a half, or half value, because that'll make this 0, and that gives me a fourth. Anything else you do is just going to make this way too crazy. And when p is a half, q is a half. So there's 3 minutes of why p and q a half, for no reason whatsoever. If you hate algebra, I'm sorry, I just ruined your day. Okay, hopefully I didn't ruin your day. I don't know. It takes a lot to ruin my day. Anyway, I had to talk to a mechanic today, so my day sucks. Alright, so these Minitab questions are very, very much like what we just saw. The big thing is make sure you use Minitab to help you. Don't do your homework in the blind. Okay? I know MyStatLab, you think that you just do it on MyStatLab, but like I suggest you like dual screen it like I got going here. Like Minitab there, and then your MyStatLab right here, and then just use it to help yourself. Okay? So here we're going to construct a confidence interval for the mean mu using confidence level 90%, sample mean 6.7, and then population standard deviation 0.6. Population standard deviation. That tells us we're going to be using a z, not a t. And then there's my sample size. So here we'll just go to Minitab and do stat, basic statistics, 1 sample z. Got to put all my stuff in here. Got my sample size right there, 46. Got my sample means 6.7. Got my known standard deviation to be, where is that? 6.6. Ooh, almost put the wrong value in. That would have been super wrong. And then my confidence level is 90%, so we'll hit options and change that to 9. Oh, evidently my last one was a 92. Good times. Make sure this is a not equal to also, so you get really weird results. We'll hit OK, and then hit OK. And then I said that really fast. Make sure it's a not equal to, because otherwise you only get one of the upper bounds or the lower bounds, not both. Alrighty. Boy, this is going to be really hard to read on my screen, so I'm hoping you have this open. I'm sorry that this is so tiny, but I literally copied and pasted it so it looked exactly like what your questions look like. A direct mail advertiser sends solicitors junk mail to thousands of potential customers in the hope that some will buy the company's product. The response rate is usually quite low. It's sad but true. Suppose a company wants to test the response of a new flyer and sends it to 1,040 people, randomly selected from their mailing list over 200,000 people. Wow, that number was hard for me. They get orders from 133 of the recipients. Use this information to complete parts A through D. The first part of this question is asking you, hey, what's the 95% confidence interval for the percentage of people that the company contacts who may buy something? Now, this is a complicated question. They only got 133 orders from their sample. Hold on a second. My computer's yelling at me again. Come on. Are you guys seeing this? I hope you're not. Yes, I can see the window running. Yes, I can see the window running. Why is this doing this? Hold on a second. Sorry, guys. And we're back. Sorry for the technical difficulties. Hopefully they will not arise again. I don't even know if you guys could see what was happening. Hopefully not. It looked weird. Anyway, so what we want to do is we want to find the confidence interval for the percentage of people of the company contacts who might buy something. So it's not all the people they contact, it's just the one they contacted through this test sampling. So we want to be using our 1040 as our people that we are our sample size, and then the 133 is our number of successes. So we're going to go up to STAT, basic statistics, down to one proportion. And here we're going to be putting in our 133 to 1040. And we want a 95% confidence interval. We're going to hit OK. OK again. Yay! So there's our confidence interval for the proportion. Be careful with your rounding here since it only wants one decimal place. So 10.8 up to 14.8. Again, remember, make sure you use the normal approximation here. Otherwise, this comes out much larger and it gives you the incorrect values. Anyway, so I'm going to talk you through all of these answers and why they're wrong really quick. The first one is the values for the interval bounds should be subtracted from 95% to obtain the company's true confidence level. That's just nonsense. So remember, confidence level is you figuring out how far out you need to go to make sure you capture the sample mean 95% of the time. I'm sorry, not the true sample mean, the true mean 95% of the time. So why are we subtracting from confidence? That doesn't make sense. Anyway, the company is 95% confidence. The probability of a randomly sampled person will respond to the flyer within the confidence interval bounds. Now, this is not a probability calculation. It's using the 68, 95, 99.7 rule to determine how far out you need to go to make sure that you get the true population proportion, the actual percentage of people who actually contact from the people the company contacted that buy something, which has nothing to do with randomly sampled people. That's a normal probability calculation. It's not the same thing as a confidence interval. So the company is 95% confident the percent of people who will not respond to the flyer will fall, there it goes again, within the confidence interval bounds. What? Not respond? That's the opposite of what we're interested in. Shuckly doodles, that's so not it. Anyway, what we're interested in is people who do respond, which is what this last one is describing. The 95% confidence interval, the percentage of people who will respond to the flyer falls within the confidence bounds. There you go. All right. Explain what 95% level confidence means. About 95% of all random samples of size 1040 will produce the interval that do not contain the true proportion of people who respond to the new flyer. That's crazy. Okay, so the big problem in here is the do not. So it's not the do not that it doesn't contain, it's that it actually contains that. This is the percentage that your likelihood that you are going to capture it. Anyway. And it's not, so B, 95% of all random samples produce intervals that will contain the true proportion. Now, it's not all possibilities of all samples, it's just samples of that size. So there's a lot going on with the confidence interval that's a little subtle, and that's one of them. It's only samples of similar size. So if you remember back when I was doing the notes, I was using random generation, but I was always generating samples of the same size because that was the only way that you could guarantee that they all would behave the same way. Okay. And it's not all people sampled. It's just not. Anyway, so the company must decide whether or not to do a mass mailing. The mailing won't be cost effective unless they produce at least a 6% return. What does your confidence interval suggest? Well, those are both bigger than 6%, so do it. I don't know why that was so dramatic. It'll be okay. One of these days I'll calm down. I need to lay off the caffeine probably. All right. Onwards and upwards. All right. So now we are on the last question. This is probably my least favorite question. I probably shouldn't have put it last. We'll see. So use the standard normal distribution or the t-distribution to construct a 95% confidence interval for the population mean. Justify your decision if neither distribution can be used, explain why, and interpret the results. In a random sample of 21 patients at the hospital's minor emergency department, the mean waiting time before seeing a medical professional was 21 minutes and the standard deviation was 9 minutes. Assume the waiting times are not normally distributed. So we got some issues here. It's not normal. My sample size isn't big enough, and I don't know what the population proportion looks like. Ay, ay, ay. So, if it was just at least 30 people, I could use t. It's not. And if it was the population's standard deviation, not the sample one, I could use t. And since I have neither of those, I definitely can't use z. And it's not normal. It doesn't do anything we need. So this is definitely like, hey, I can't do this. So cannot use the standard normal distribution or the t-distribution because I don't know the population standard deviation, also known as sigma. I don't have a sample size that's big, and the times are not normally distributed. Now, if I didn't have either of these and I knew that it looked normal anyway, then the sampling distribution would look normal, and I could still do this. But I should probably use the t. But I can't do any of this. So, I can't do the 95% confidence interval, so neither distribution can be constructed for the confidence interval. And then I can't interpret the results because I can't use either of them. It's sad but true. You have to watch out for this. It is quite possible if your sample size is too small and you don't know the population standard deviation, then you can't do either of these. So now you know, and knowing is half the battle. I hope you enjoyed today's video. Now I gotta try to make it pause. And we saw how long that took me last time. Hope you're enjoying statistics. I'm still sick as a dog, so I sound funny to me. I wonder if I sound funny on here, too. Maybe if I shrink this. Look, camping. Nope, it's not here. Here's another fun stats program while we wait for this.